Alright, so in this video what I'm going to do is I'm going to talk about instantaneous velocity. Instantaneous velocity comes out to be a very specialized form of a more general term of average velocity, which is something that we have already discussed in our previous videos. So let's go back to that diagrammatic representation of instantaneous velocity. Let me get rid of this for a moment. And alright, so in order to define velocity, we had to define position vectors and then displacement vectors, which turned out to be the difference in two position vectors. So assuming that a body takes the following path, like so, and we chose 2 points, point A and point B, like so, and we ended up drawing position vectors from a reference point, the origin. So the first position vector was in this direction all the way till A, so that was OA vector. This was a position vector at, say, time t. So the body was at point A at time t, and then the body proceeded on to move along the trajectory and moved till point B. And when it reached point B, we defined a new position vector. So that was O to B, that was this position vector. And assuming that the motion from A to B along this trajectory took the body delta t amount of time, the body was at B at t plus delta t time. This is absolute time. And therefore, the position vector changed to R of t plus delta t, which was OB vector. Now, with these two position vectors, what we did is we subtracted them, so we ended up getting another vector which we call the displacement vector, or d. And the way to represent d was d, or the displacement vector, was r of t plus delta t minus r of t. That was your displacement vector. But we notice that displacement vector gives us a direction of movement in terms of vectors. But it turns out that the body has nothing to do with this displacement vector when you're connecting points A to B on the trajectory. Because the body is taking the path from A to B via this curved trajectory. It's not going from A to B directly. So there needs to be some sort of modification in the definition of displacement vector to include this trajectory. And we do that by assuming that our delta t is very small. Now, if delta t is very small, oh, there's 3 L's there. So if delta t is very small, then what happens is that if A is a first position vector and our second position vector is very close to our first position vector, so if this is point A prime, now the difference in A and A prime is, say, dt. Now this is just another variable. This is just a quantity like delta t, but because I've used delta t here, I'm going to use dt there. So dt is the time the body takes from A to A prime along the trajectory. So that means this vector of OA prime becomes a position vector at time t plus dt. And OA, as it were previously, is the position vector at time t. Now, when dt is really small, when dt is very small, then if you notice, r of t plus delta t plus dt minus r of t gives us a new displacement vector. I'm going to draw that in red now, and which is this. This becomes a displacement prime vector. And if you notice, the displacement prime vector closely resembles the direction of the body, direction of the trajectory. That's because if you measure the trajectory at very small instances of time, that trajectory ends up following the actual path of the body. So it's as though you are watching the motion of this body at really small intervals. So if the body was at A, it was here, at A prime it was there, say another point it were here, and maybe at some other point it were here, and so on and so forth. If you notice that these displacement vectors, which end up forming by connecting these adjacent dots closely resemble your actual trajectory. So that's a good thing. We are coming close in approximation. Unlike this displacement vector drawn in green, which does not really resemble the motion of the body. However, these small displacement vectors end up closely matching what's happening to the body in that small duration of time. So it's good to work with a small dt, or in other terms, it's good to work with a small delta t, because if you reduce delta t to dt, you get this equation. So our displacement now matches the path, and that's a good thing. And what we can do is we can take this d prime vector and define a corresponding velocity. Now remember, in a previous case when we took this d prime vector and we divided this d prime vector by, let me do that here, we divided d prime vector by the time over which we measured the d prime vector, that gave us an average velocity. Now average velocity was just a vector corresponding to this displacement vector. But if the displacement vector in the first place did not match with the trajectory of the particle, then defining this average velocity was also in a hypothetical term. It really didn't mean anything. However, when we reduce our limit of delta t to dt, the d prime vector, or the new displacement vector, which matches very closely to the actual path taken by the body, ends up giving rise to this new definition of velocity, which closely resembles the velocity of the particle. So if we divide d prime by the dt velocity, this gives us the instantaneous velocity we have been looking for so far. So that's what happens. Now remember, when dt is really small, r of t plus dt and r of t, these two vectors are very close. And when they are very close, this term here is very small. So that means our instant velocity has a potential of being really small as well. But remember, when dt itself is very small, you're dividing a small quantity on the numerator, which is small, by a small quantity on a denominator, which is also small. And by division of two small quantities, you end up getting a decent quantity, a quantity of a decent magnitude. And so this average velocity is not what many mistakenly think of it to be, a very small quantity. It's in fact the actual velocity of the particle at that instant of time. So if we draw that diagram once again to really understand what's happening here, let me draw coordinates again, like so. The path taken by the body, like so, and my two displacement vectors. Now, these two displacement vectors are, as what we've already agreed, should be very close to one another. So this is my first displacement vector right there, OA, and my second displacement vector right there. So that's, let that be, say, B. The time that the body takes from going to A to B is dt. So if A was measured at time t, B would have been measured at time t plus dt. So you have two displacement vectors, r of t and r of t plus dt. Remember, dt is really small. So our displacement vector, which is a very small quantity because these two vectors are very close to one another, points along the approximate direction of motion in that time interval. And we, instead of representing it as d prime as what we did in the previous diagram, let's call this your delta ds, or ds vector. So ds vector is a very small displacement vector, and it's small because dt itself is really small. So ds will therefore be r of t plus dt minus r of t. That is how we define our very small displacement vector. Now dividing the entire equation by 1 by dt, or the time interval, we get ds vector by dt becomes r of t plus dt minus r of t divided by dt. Now, if you take a close look at this, the left-hand side is something that we define as instantaneous velocity. So that's what we have been looking for so far, a velocity that closely resembles the motion of the particle. And this is the formula for finding out instant velocity. And if you look at the limit in which we evaluate this side of the equation, the limit is that dt goes to 0. dt is very, very small. So if dt is very, very small, then this term becomes the instantaneous velocity, or we call that the velocity at time t, and that has the form of the following expression. So this is how you would find the instantaneous velocity if you know the trajectory of the particle. But what does this term here represent? Well, this term represents the difference in the position vectors of the trajectory of the particle divided by dt. Now, if you go back to your calculus and you look at the formula for the derivative of a function, this here closely resembles the derivative of the position vector. So in order to redefine v of t, that is the instantaneous velocity of the particle at time t, we use this notation as well, which states that the instantaneous velocity of the particle ends up being the derivative of the position vector of the particle at that time. So that is how you would go and define your instantaneous velocity. Now, like average velocity, instantaneous velocity matches the direction of your displacement vector. So in this case as well, instantaneous velocity should also match the direction of ds vector. Now, if ds vector is pointing in this direction, instantaneous velocity therefore would also point in this direction. It would point in this direction as well. Now, if you notice why I have drawn the velocity vector much longer than ds vector, is that's because when you divide the vector by a very, very small quantity, you end up getting a very large value, or a decently large value in this case, because the numerator itself is really small. So that kind of compensates, and that is in fact the basis of calculus, and that gives you a finite length worth a vector. That is what we call the instantaneous velocity. Now, if you extend this discussion to different points on the trajectory, you would notice that at this point, if you were to evaluate the instantaneous velocity at this point would point in the following direction, very closely in this manner. And this direction very closely will represent the tangent of this white function, like it did in this case. And if you were to do the same thing there, well, the tangent would be in this direction, therefore the velocity must also point in this direction at that point of time. So that is how you go and define instantaneous velocity for a particle moving in a certain trajectory at that instance of time. And you use the definition of derivatives, which is given in calculus as the derivative of the position vector at that instant of time. So this is basically an extension of the average velocity that we defined in our previous videos, and it uses just a different magnitude of time to give rise to an instantaneous velocity, which closely resembles the actual motion of the body. So I hope this video made sense. I hope it helped you understand the importance of defining instantaneous velocities and its difference from average velocities as well. And we're going to do a small problem based on this difference, which will help us furthermore in terms of understanding of the difference between average and instantaneous velocities, and also the importances as well. So I hope this helps, and all the very best.